Welcome to the wonderful world of physics. This is the Chapter 17 homework for Physics 102B. We start with number 35. Find the resistance between the two ends of an aluminum wire, 0.25 meters long and 1 centimeter in diameter. We have the length here and the radius of 0.5 centimeters given. We want to know the resistance. Resistance is resistivity times length over area. It's a circular cross-sectional area, so we'll change area into pi r squared. We need to find the resistivity of aluminum. We can look that up in the table in the book, 2.75 times 10 to the negative 8 ohm meters. Then we have times the length divided by pi r squared. Make sure we have that in meters. And we get an answer of 8.75 times 10 to the negative 5 ohms. Number 36. A platinum wire is originally 20 degrees Celsius. Find the temperature required to raise its resistance by 1% and by 10%. So we want to know the temperature. Let's solve that for T. And when you algebraically solve for T, you should get this R. You start by dividing by R naught, subtracting away the 1, dividing by alpha, then finally adding T naught. And so here's our equation for T. Now for part A, if we are raising its resistance by 1%, that means that the ratio of R over R naught, or the new resistance over the old resistance, is 1.01 because it's 101% of what it used to be. So we plug that in for R over R naught, and we're going to need the alpha for platinum. And don't forget to add the T naught, the room temperature, 20 degrees Celsius, and we get a temperature of 22.56 degrees Celsius. So by raising the temperature just a couple of degrees, we get this 1% increase in resistance. We can do the same thing in part B, where we're raising the resistance by 10%. So R over R naught is 110%, or 1.10. We plug that into the equation, and we get a temperature of 45.64 degrees Celsius. Number 38. An electron beam carries 1 milliampere. How many electrons pass a given point each second? Since current is charge over time, we want to know what the total charge is. So charge is current times time. And the total charge is going to be the number of electrons times the charge on each electron. So here I've made the number of electrons n times the elementary charge. Now we have Ne equals I times T, and we'll solve for n. N is IT over the elementary charge. I plug in the values, 10 to the negative 3 amperes times 1 second, divided by the elementary charge, 1.602 times 10 to the negative 19 coulombs, and we get 6.2 times 10 to the 15 electrons. Number 42, another question about time-dependent resistance. A nichrome toaster wire, initially at room temperature, carries 2.75 amperes immediately after it's turned on. After the wire heats, the current drops to 2.46 amperes. What is the temperature of the nichrome then? Well, let's look at the relationships. We know this equation that we got in a previous problem, the temperature related to resistance. And ultimately, we want to solve for temperature. But now we want to think, what is the new resistance over the old resistance? What we're given is the currents. And so let's think about how we can turn the information involving current into resistance. We're going to use Ohm's law, that the current through the resistor is V over R. And voltage is going to stay constant. So the resistance, the new resistance, is voltage over the new current. The old resistance is voltage over the old current. And if we make a ratio between those two, new resistance over old resistance. Now, why are we doing that? Because in the formula up at the top, we're given R over R naught. So let's see what happens to R over R naught when we put those together. We make the ratio V over I divided by V over I naught. And so here I have times I naught over V. The voltage divides out, and we're left with that ratio. R over R naught is I naught over I. So now we're going to take that and plug that into the equation at the top of the page. And now we have temperature is I naught over I minus 1 over alpha plus T naught. So we plug those in, the old current and the new current. It is nichrome, so we look back in the table. In chapter 17 for the temperature coefficient alpha of nichrome, and it says 4.1 times 10 to the negative 4 per Celsius degree. We plug those in and we get 308 degrees Celsius. Number 52, combining resistors, a 34 ohm resistor and a 45 ohm resistor are in series. Find the equivalent resistance. So for part A, with series resistors, the equivalent resistance, you just add them up, so 79 ohms. For part B, find the current when the series combination is connected across a 7.5 volt battery. We'll use Ohm's law, where the current is the 7.5 volts over the equivalent resistance, 79 ohms. So we get 0.0949 amperes, or we can say 95 milliamperes. Number 53 is a problem involving resistors in parallel. They are 250 ohms and 370 ohms. Part A, find the equivalent resistance. So we're going to add their reciprocals and then take the reciprocal of that. So the equivalent resistance, you should get 149.2 ohms. Part B, the parallel combination is connected across a 12-volt battery. Find the current supplied by the battery and the current in each resistor. The current supplied by the battery, we'll use Ohm's law, is the voltage divided by the equivalent resistance that we found in part A, and we get 0.080 amperes. Now we want to know the current through each resistor. Now if they're in parallel, each resistor has the same voltage. It's going to be 12 volts. So we're going to use Ohm's law and apply it to each resistor. For the first one, the 250 ohm resistor, the current going through it is the 12 volts divided by 250 ohms, and that's 0.048 amperes, or 48 milliamperes. The second one is 12 volts over 370 ohms, or 0.032 amperes. Notice that they add up to the total that we got at the beginning of part B, which is 0.08 amperes. Problem number 69. Says a hairdryer consumes 1750 watts when connected to a 120 volt source. Find the current in the hairdryer, how much energy is consumed if it runs for 10 minutes, and compute the monthly cost if the hairdryer runs for 10 minutes each day at a cost of 15 cents per kilowatt hour. So for part A, we find the current. Well, power equals current times voltage. Let's solve for current. Current is power divided by voltage. And when you divide those, you should get 14.58 amperes. The energy consumed in 10 minutes. If power is energy over time, then energy is power times time. So it's going to be 1750 watts times 10 minutes is 600 seconds. So we get 1.05 times 10 to the 6th joules. We're going to need that answer for part C, because part C says, what if we do this for 10 minutes for an entire month? How much is it going to cost? So in part C, at 15 cents per kilowatt hour, well, let's first figure out how much energy that's going to be. Let's assume in the month 30 days. And so it's going to be 30 times 10 minutes a day, and we found in part B 10 minutes is 1.05 times 10 to the 6 joules. Multiply that by 30, and that gives a total energy for the month of 3.15 times 10 to the 7th joules. Now, the cost rate is given not in terms of joules, but kilowatt hours, which is a unit of energy. So it's helpful to think of a joule as being a watt second, because remember, a watt is a joule per second, so a joule is a watt second. Let's take this amount of energy, 3.15 times 10 to the 7th watt seconds, divided by 1,000, that's times 10 to the 4th kilowatt seconds. So that's where I've started up here with the unit conversions. It's 3.15 times 10 to the 4th kilowatt seconds, but we want to relate this to kilowatt hours and throw the dollars per kilowatt hour in there. So let's make the seconds divide out. We multiply by 1 hour over 3,600 seconds, and that'll give kilowatt hours. Finally, we're going to do dollars divided by kilowatt hours. And you can see all the units of kilowatt hours, those divide out, and we're left with dollars. So we get a cost of $1.31 for the month's usage. Number 74, how large a capacitor should you combine with a 450 kiloohm resistor to make an RC time constant of 25 milliseconds? Remember that the time constant, I use the letter tau here, is R times C. It wants 25 milliseconds. That's 25 times 10 to the negative 3 seconds. We're given the resistance of 450 times 10 to the 3rd ohms. So if the time constant is R times C, then C is time constant divided by R. We'll plug in those values, and we get 5.5 repeating times 10 to the negative 8 farads. So let's round that to 5.6 times 10 to the negative 8 farads, or 56 nanofarads. Number 75. A 300 picofarad capacitor, initially uncharged, is in series with a 175 mega ohm resistor. So here we have an RC circuit. The series combination is then connected across a 6-volt battery. Find the charge on the capacitor after 1 millisecond, 10 milliseconds, and 100 milliseconds. It's useful to first find the time constant RC. And so that's what I've done here first. After listing out the given information, when you multiply R and C, you get 0.0525 seconds, which is 52.5 milliseconds. So if it's 52.5 milliseconds, that gives you a feel for, in parts A, B, and C, how much charging we can expect to have occurred. Without doing any math, if the time constant is 52.5 milliseconds, then for part A, 1 millisecond, it won't have charged that much. 10 milliseconds, it won't have charged too much, but it's getting there. 100 milliseconds is about 2 time constants, so it will have charged a good way. Well, now let's actually do the math. We're going to use the equation that the Q as a function of T is EMF times capacitance times 1 minus little e, the natural log base, to the negative T over RC. Now, if you want to, it might be more convenient now that we've computed RC up here just to type into the calculator 0.0525. However, I've written it all out. You can see it gets kind of small print cluttery right here, but I've written it all out with the voltage, the capacitance, and all those numbers that go into it. And notice that for part A, the time is 10 to the negative 3 seconds. When you compute all these, I've kept the ratio that's in the bracket separate. The E exponent term becomes 0.9811. When we subtract it from 1, it gets 0.0189. That means that it's only 1.89% of the maximum charge, the total charge that it's eventually going to get. We multiply times E times C, which is going to be the total charge it's eventually going to get, and we get 34 picocoulombs. For part B, we do the same. When we do that, the bit in the brackets becomes 1 minus 0.0 0.8266, which means it's only going to be 17.3% of its final charge, or 312 picocoulombs. Finally, for part C, we're using, part C says 100 milliseconds or 0.1 seconds, and when you run the numbers, you should get 1.5 nanocoulombs. It is 85.1% of the maximum charge. For number 78, a 25 nanofarad capacitor is in series with 1.45 mega ohm resistor. The capacitor is initially uncharged when the series combination is connected across a 24-volt battery. What is the maximum charge the capacitor will eventually attain? How much time does it take for the capacitor to reach 90% of that maximum charge? Down at the bottom of the screen, you can see the graph, the charge as it increases, and there's after one time constant, after two time constants, etc. By the time it gets to 5 time constants, it's pretty much all the way charged. Let's actually do the math. The maximum charge is going to be voltage times capacitance, as if the resistor weren't even there, because the resistor adds the exponential, the upside down exponential decay function, but for a very, very long time, that whole part just goes to 1. And so for part A, you should get 6 times 10 to the negative 7 coulombs. Now for part B, that's asking how much time to get to 90%. So let's look at the equation that I've done here. If we do Q equals Q max times the exponential function, divide Q by Q max, and we get 90%. So 0.90 equals the bit in parentheses, 1 minus e to the negative t over RC. Now we have to algebraically solve for t. So I've moved e to the negative t over RC. I've added it to the left-hand side. I've subtracted both sides by 0.9. So the right-hand side becomes 1 minus 0.9. And so we get this term, e to the negative t over RC is 0.1. If we want to solve for t, we have to turn that into a logarithmic equation. So the log of base e, which means natural log, of 0.10 equals the exponent, negative t over RC. From there, solve for t. So t is negative RC times the natural log of 0.1. Plugging in the values for r and c, we get 0.083 seconds, which, by the way, is about 2.3 times the time constant. Now we can look at the graph and see it's about right here. So it's about, and that's where we can see it's about 90% charged. And that is the end of the Chapter 17 homework. Have a great day.